Alrighty, folks. Back here, I want to do one more quick video for you. I hope it's quick. My last video was pretty quick, and I have again another short topic that I kind of want to get into it with you in this video. Particularly since we are fresh using substitution method. We want to be careful, right? We are going to want to be careful using that substitution method. There are a lot of functional forms that when we apply substitution method to those forms, we encounter some interesting results, right? We encounter, I won't hold back here. What we encounter are what are called indeterminate forms, all right? And we're going to need to be cautious when working with indeterminate forms because, as the name implies, they are a form that we encounter for a value where we can't determine the value from the form. Indeterminate forms. If we look here at this specific example, right? I always talk about consider evaluating a rational function like this. The limit as x approaches 2, right? For x minus 2 divided by x squared plus x minus 6, right? If we attempt substitution method, we're going to substitute in that value of for 2 into each of the locations for x. We can see right away in the numerator, if we substitute in the value of 2, we have 2 minus 2, which yields a value of 0 in the numerator. And if we substitute in a value of 2 into the denominator, we end up with 4 plus 2 minus 6, which is also equal to the value of 0. Substitution method is actually going to produce the result 0 over 0. So I throw out the question, what is the value of 0 over 0? And I have a lot of novice calculus students who, without much experience, will give you a lot of, could give you potentially several different answers. Some would like to argue that when you take a number and divide it by itself, that is always equal to 1. Like 5 divided by 5. 5 divided by 5 is 1. 4 divided by 4 is 1. Negative 6 divided by negative 6 is 1. Pi divided by pi is 1. What about 0 divided by 0? That should be 1, right? I'd be cautious saying that. That is not necessarily correct, right? And I say it that way for a reason. And I'll get back to that. Some students like to argue for the value of 0 over 0. Well, since I have a 0 in the denominator, I know every time I divide by 0, that result must be undefined. So they like to try to argue that 0 over 0 is undefined. And again, I say be careful there, because that might not necessarily be true for this value of 0 over 0. And then lastly, a lot of novice students like to answer, well, you have a 0 in the numerator. And I know anytime 0 is divided by a number, the result is 0. And as I've been, I'll again say be cautious. That's not necessarily true for the result of 0 over 0. And I say it that way because, again, 0 over 0 is what we refer to as an indeterminate form. We can't draw any conclusion about its value from the form. It could be equal to 1, but I don't know. It could be equal to 0, but I don't know. It could be undefined, but I don't know. It could be any real number, I don't know. It's what's called an indeterminate form. The value that it represents cannot be determined from the form. All right? That's what we refer to as indeterminate forms. Now, I get a bit into that explanation here, right? Some may argue 0 over 0 is 0, or they might say it's 1, or it's undefined. However, none of those are true, right? And any one of those results could be possible, right? And the result of 0 is known as the indeterminate form, and you can see all that, right? And then I get a bit more specific, and I point out there is more than one indeterminate form. 0 over 0 is just one case of an indeterminate form. There are others. And that's what this definition highlights, right? An indeterminate form is a value expressed as one of the following mathematical statements here. And you can see these different statements, right? And then I finish by saying the value expressed in one of these formats cannot be determined from that format, right? That's what we've said about 0 over 0. Its value, when we encounter it in substitution, cannot be determined from that format. Plus or minus infinity over infinity. You could have a plus or a minus infinity in either of those numerator or denominator, and you would have an indeterminate form. We just summarize that as plus or minus infinity over infinity. Infinities divided by infinities are indeterminate statements, right? Are indeterminate forms. Again, we get a similar argument to 0 over 0. Some might like to argue 1. Some might like to try to argue 0, right? That's a hard argument to make for the form because it's indeterminate. Infinity minus infinity. That's an indeterminate form, right? Can't say what that is from the form. Some students will say, well, isn't it just 0? And I'll say, okay, well, that depends. If you go infinity that direction and you take away infinity that direction, aren't you really just infinity in that direction? I don't want to make that argument either because that's what's known as an indeterminate form, right? 0 times infinity, and that could be plus or minus, and maybe I should include that there. Plus or minus infinity, right? 0 times a positive infinity or 0 times a negative infinity is an indeterminate form. 0 raised to the power of 0. 1 raised to the infinite power, or infinity raised to the 0 power. Those are all examples of indeterminate forms, right? You want to begin to familiarize yourself with this list. If your evaluation of a limit is producing a substitution result that involves zeros or infinities, or you want to be cautious with this case of 1 raised to the infinite power, that's the one case that involves something other than 0 or infinity. You want to come over and check your indeterminate forms. All right. Right now, we have some methodology for working with these two forms. All right. We developed some of that methodology here when working with discontinuities and when working with that instantaneous velocity calculation. If we go back and look at substitution method, we've had some 0 over 0s in those cases. And we had a way to handle that. And limits at infinity produce infinity over infinity results. And we have a method to still work through those and find our value. The rest of these formats, we're going to develop methods later on towards the end of chapter 4. There is a technique for evaluating limits that we're going to learn a little later on because it actually requires us to use what we call a derivative calculation. And we got to learn about the derivative before we can learn about the methods we could use to evaluate these indeterminate forms, or limits that yield these indeterminate forms. There's some techniques referred to as L'Hopital's methods. And there is a rule that's referred to as L'Hopital's rule. And we're going to learn L'Hopital's rules and methods to help us evaluate limits that produce these collective set of indeterminate forms. What we're going to find is we have a rule for the first two, and then we have some methods that involve the rules for the last, 5 cases seen here. All right. But you want to start to be cautious of these situations when you're running substitution method to evaluate a limit. Currently, you'll probably only encounter these first 2 cases. It wouldn't be fair to ask you to evaluate limits that produce these other situations quite yet. It's not until we talk about L'Hopital's that we'll see these cases particularly. So I say all that right here in this note. And then this follows with just, I think, a little bit of example. If we go back and we consider our case, right, and we think about why substitution method produces that result of 0 over 0, it is because in the numerator and denominator we encounter that common factor of x minus 2. And if I take note of the denominator, in the denominator, if I was to factor that quadratic, I do believe I'd also encounter that linear factor of x minus 2. And that's what we notice here. That if I factor this denominator in our function f, I will obtain x minus 2 times x plus 3, where this common factor of x minus 2 in the numerator collectively will cancel with this common factor of x minus 2 in the denominator. And when that does, that leaves me with the result of 1 over x plus 3. Where we can end up saying, in a sense, f must be then equal to 1 over x plus 3 in its simplest form, canceling that common factor of x minus 2 in both the numerator and denominator. So if I go back and I replace that into my limit here, all right, I see that is what I end up doing here in my limit calculation. And I now consider substitution method. Substituting in for that value of x, the value of 2, I no longer have that indeterminate form as a result. I encounter the value of 1/5. All right, 1/5 is the value for that limit, right? And there's no way we could have told ourselves that 0 over 0 was actually equal to 1/5 from the form 0 over 0. And notice it's not 1 or 0 or undefined in value. It's the value of 1/5. All right. Now, in this case, the indeterminate form was due to what we call a removable discontinuity at that value of x equal to 2. And that's exactly what we did up here to go from this step to this step, right? From this result on the left to this result on the right, is we removed that discontinuity that was at the value of x equal to 2. Right? And that's what allowed us to evaluate this particular case. Now, I do have here one other example that produces the indeterminate form of 0 over 0, where we do not have a removable discontinuity. You can't always expect a discontinuity to be removable, as we had seen in the previous case. That worked nice because we were dealing particularly with a purely rational function. What we see in this next limit, the limit as x heads to 0 for the sine of x over x, is that is a rational form, but it is not purely a rational function. We have the form of a ratio, a numerator and a denominator, but you notice in the numerator you don't have a polynomial. You have a trig function. We have the sine up there in the numerator. And when we apply substitution method, we're still going to get 0 over 0. The sine of 0 is equal to 0, and x evaluated at 0 is 0. Right? Again, we're going to get 0 over 0, but there's no common factor of x to cancel between the two. I just can't cancel that x inside there with this x. Unfortunately, this x inside here is actually within the sine argument. And there's no easy way to remove it from that without also algebraically impacting the x in the denominator, and it would change its value. All right. We don't have a common factor to cancel like we did in this case to remove. So to evaluate this limit in this case, we do have a bit of skill that we can rely on. And what we have is a technique known as the squeeze theorem. All right. This is usually a good spot to talk about the squeeze theorem. When talking about this, introducing ourselves to this indeterminate form, 0 over 0, and how in purely rational forms, when we encounter it, we have the case for a removable discontinuity. But in the case for sine x over x, we don't. And what technique could we use to thus then evaluate that indeterminate form? Well, here we have squeeze theorem. All right. Here's the squeeze theorem. All right. Probably should title that squeeze theorem. Right? And what we assume here to begin with is that we're looking at classically the limit as x approaches a for f of x. Right? We maybe even should set that up. Consider the limit as x approaches a for f of x. Right? We might say here, assuming f of x, right, the argument of the limit we're considering is trapped between two other functions. On the low end by function g and on the high end by function h. F of x is always going to be between those two with these inequality statements. And we're going to assume that for these values of x in each of these functions, right, near the value of a. And if this setup is true, if this assumption is true, then what also is true is that the limit applied to all three parts of that inequality, the outside functions and the inside function to this inequality, right? Then that inequality statement remains true. In a sense, if f of x is stuck between g and h, then the limit of f is stuck between the limits for g and h. And what this gives us is what's referred to as the squeeze theorem. The idea being that even though f is not g or h per se, it certainly is stuck between those values, that if I was able to show that these two outer limits were equal to each other, then I would be able to conclude that this inner limit here, the one with respect to f, right, would be equal to the result of these outer two limits. Due to the fact that what would be happening is the result for this limit would be being squeezed by these two functions as we get near a with our values of x. It's called the squeeze theorem. And here's an illustration of what we mean. Right? We might consider the sine x over x near x equal to 0. What we can actually show with this result sine x over x is that it's stuck between two functions. It's always going to be bigger than or equal to the cosine x. And we could show that it's always going to be smaller than or equal to the result of 1. Can I highlight it? The sine x over x is always stuck between these two results. And you go, well, how do we know? And I can say, I can show you this graphically. Here's a graph of that situation. Right in the middle, in this blue graph, if you can see that color, that is the graph of f, the sine of x. Cycles from negative pi to pi. Hold on here. Do I have that right? Oh, yeah. I got to fix this graphic. This graphic is supposed to be illustrating sine x over x, not sine x. Because that is so. Yeah, I need to fix this graphic real quick. Give me 2 seconds in the land of pause. So let me pause this. All right, I'm back. It was a quick fix, folks. The graphic was accurate. What was inaccurate, was the picture is accurate. What was inaccurate was the label. I knew that wasn't the sine function in blue. That is actually the function, the sine of x divided by x. So I just changed that real quick in the graphic. That's all I had to do. And I'll show you how I do my graphics some other time. But we can see that this function sine x over x, when we are near the value of 0, the center of our graph, right? And here I'm showing you from -3 to 3 for values near it. That blue graph for the sine x over x is always smaller than the value of 1. It's always less than 1, which is highlighted by this green graph, this constant graph that's at a height of 1 along the vertical axis. And it's always larger than the cosine of x, the graph seen here in red. And what this illustration helps to highlight is where it gets its name squeeze theorem from. Because in all three of these graphs, as we get closer to the value of 0, right, from both the left or the right-hand side, we can see that the graphs themselves are squeezing, right, that blue graph in the middle particularly, into the value of 0. We don't know this limit, right? We might say we don't know the limit of the blue graph, but we do know the limit of the cosine graph. Cosine its limit at 0 is 1. Cosine of 0 is 1. We do know the limit for 1 as x heads to 0. It's also the value of 1. So if the sine x over x is stuck between these two functions and both of these limits approach the value of 1, then the graph for the sine x over x, or the function sine x over x, must have its limit squeezed between those two values, or in a sense, set also equal to the value of 1. And that's what we see here in this case. All right, my apologies. From the squeeze theorem, we can say that the limit as x approaches 0 for the cosine of x must be less than or equal then to the limit as x approaches 0 for the sine x over x, which must be less than or equal to the limit as x approaches 0 for just the constant value of 1. Where we can simplify that pretty quickly, right? Evaluating the limits on the outside, we know the limit for the cosine of x at 0 is 1. We know the limit of 1 when x is 0 is also 1. So if the limit as x approaches 0 for sine x over x is greater than or equal to 1 and less than or equal to 1, there's only one implication we can draw from that, and that is that its value must also be equal to 1. Right? And we do see again that supported right here in the graph for that function, sine x over x. As we approach 0 from both sides, it does appear that we're approaching the value of 1. I do believe that's where we end. I think we have two special limits that are trig limits. This is one of them. We're actually going to encounter this limit again. These are unique trig limits, and actually here's two of them. My apologies, we just hit the end of the notes again. Right? But these two unique limits are two unique cases, right, where we do not have a removable discontinuity. If you notice, we just examined this case. We can show something similar for this case too. And notice that discontinuity is not removable. You still get 0 in the denominator when you substitute. And in the numerator, the cosine of 0 is 1. So 1 minus 1 up in the numerator also yields 0. And there's, no common factor to cancel. Which you could show through another squeeze theorem is that all of that is equal to the value of 0. Right? These are two unique limits that do not have removable discontinuities. And where substitution method in both would produce that indeterminate form 0 over 0. These are actually two unique limits that we show at this point in time because we're going to come back and rely upon those results in some proofs in our next chapter. All right. That's it for this set of notes, folks. Like I said, it was another short set. What I have left to do, I think I have a set of notes I want to go over with you that gives you a whole bunch of rules or laws for limits. And we will see those laws worked into a few examples along the way. All right. And then collectively, at that point, my hope is that we have a pretty decent study of what is a limit and how do we evaluate a limit and what are some rules involved with evaluating limits. You might think of these as the first two rules. These are two rules kind of for you, a unique case though. Right? We're going to add a whole bunch more to these. We're not quite done, however, though. What we still got left to talk about in Chapter 2 after we wrap up all the rules is we have to get into what's called the epsilon delta definitions of limits. We have to actually get into what is referred to as the precise definition of limits. And that is where we're going to end our Chapter 2 experience with introducing the concept of a limit. It's a little later on, probably not this week in class, but next week, so those videos will be coming. I got one more to talk about with the rules, and then epsilon delta. And that rule video should come out sometime this week is my hope. All right. So I will see you in class, and I will see you next time. And I'll stop there. Have a good day, folks.